So what do we do about serial correlation? Again, we consider the AR1 instance because, in the next 2 minutes anyway, it's the simplest one to worry about. One way to go about it is to recall that in order to construct the efficient estimator, we have to be able to estimate the error covariance matrix. So if you take that highly patterned matrix, you take its square root, you pre-multiply all the data by the square root, then by construction you have the efficient estimator, the same way we did with heteroscedasticity. So because the error covariance matrix and the serial correlation has a very specialized structure, it turns out that the efficient estimator is to apply least squares to the transformed data set where you measure all the observations as a fractional deviation from the previous period. So the trick is to figure out rho, an estimate of rho, and then take these first partial differences in all the data. Again, fortunately, the software packages is just a button that you click and it does all those computations for you. But that's what's being done. And again, with the software packages, you have a multiplicity of ways to do it. Durbin's method, Cochrane's method, and there must be nowadays in eViews and TSP and so on and so forth, there must be a menu of 6 different ways to estimate rho and then construct the efficient estimates of the data. But the simplest ones to understand are Durbin-Watson and the brush structure thing that we talked about here. And the others all work in very similar fashions, including the maximum likelihood of discrete search methods that work on the same principle. So serial correlation, when there's serial correlation, your least squares estimator is still unbiased, but it's not efficient. We have different ways of correcting for the inefficiency. We have ways of testing for the presence of serial correlation. So next week we'll talk about method of moments. Your papers are due in 2 weeks.